Welcome to the 29th Jansky Lecture. The Jansky Lectureship was established by the trustees of Associated Universities, Inc. to recognize individuals who have made outstanding contributions to astronomy. It is named for Carl G. Jansky, the discoverer of cosmic radio waves. And it's a pleasure to have Carl's son David and nephew Curtis with us tonight. Tonight's lecturer is Dr. Vera C. Rubin of the Department of Terrestrial Magnetism, Carnegie Institution of Washington. After graduating from Vassar College, Dr. Rubin earned graduate degrees at Cornell and Georgetown universities. She has contributed much to our understanding of galaxies, and she is well known for her demonstration through optical observations of the existence of dark matter. In recognition of her accomplishments, she has received many honorary degrees and awards. Last year, she was awarded the National Medal of Science from President Clinton. The title of her lecture is, "What is the Matter in the Universe?" Please welcome Dr. Rubin.
Thank you very much. It's a great honor to give the Jansky Lecture, especially in front of so many old friends. We live in a universe which is amazingly beautiful, enormously large, incredibly complex. And one of the remarkable features, I think, is that at least some of it can be understood. And tonight, I would like to tell you what we presently understand about the universe in which we find ourselves. 60 years ago, Hubble, Shapley, and others understood that we live in a galaxy, that space is expanding, carrying the galaxies with it, the universe is expanding, and they understood this in terms of what they called the perfect cosmological principle. Everywhere, in all directions, space was homogeneous, isotropic, and smooth. And tonight, I'd like to show you the evidence that, in fact, this is not a good description of the universe in which we find ourselves. For the last 20 years or so, we have understood that at least the universe which we observe with our optical telescopes, radio telescopes at all wavelengths, the universe is very lumpy, that stars form into galaxies, galaxies clump into groups, into clusters, clusters form into superclusters. And over large regions of space, the added gravity of these large conglomeration means that large streams of galaxies are moving toward regions of higher density. That's one of the things we've learned in the last 20 years. Another thing we've learned is that most of the universe is not radiating. It's not radiating at any wavelength that we can see with our telescopes. And it is undetectable with all the instruments that we have so far been able to build. And this means that when we look at the sky, when we look at this clumping universe, we're really seeing only perhaps 10% of the universe. And my conclusions will be two, really. A very general one, that I think there is still an enormous amount to be learned. I think there are really very major features of the universe that we have not yet detected. And the second one is that all the observational evidence we see is consistent with a low-density universe that will expand forever. Even counting the dark matter, which we can detect by its gravitational attraction, we cannot count enough matter to halt the expansion of the universe. So let me start by showing you pictures of what we can see, and then go on to the question of the unseen matter. If I could have the slides, please. This is a cartoon which says, I see here that the universe is now thought to be full of inexplicably dense clumps. So it's these dense clumps that I'm going to try and convince you of. The next slide. We live in a galaxy. I presume all of you know that if you go outside on a very clear night in Charlottesville, all of the stars you see are members of our own galaxy. That means they're gravitationally bound. They're all orbiting in circular orbits, mostly circular orbits, about the center, about a very distant center. At the position of the sun, it takes us about 200 million years to go once around the galaxy. So we've been around 10 or 20 times in the age of our galaxy. The stars are not distributed at random, but they're flattened to a plane. Our sun is located in the plane, so that when we look through the plane, we see vast numbers of stars along the line of sight, and we see these in a bright band that we call the Milky Way. Could we have the lights down a little more? It was a puzzle to the ancients what the Milky Way was. It was not until Galileo built his telescope in 1609 and pointed it at the Milky Way could he say that the Milky Way was composed of lots of stars. Can you see that? No. Could we have the lights down? Could we have the front lights out? This is a picture of the, if we could have the front lights out. Thank you. Okay. So here is the southern Milky Way as you see it from Chile. We can't see all the way to the center. This is the direction toward the center. The Milky Way goes overhead. We can't see all the way to the center because the Milky Way is composed of more than just stars. There's gas and dust, very low density, but long enough path length so that it brightens, but we're not looking totally toward the center. The next slide, please. Here's a picture of a galaxy which we see with our telescopes compared to the view of our own Milky Way that convinces us we understand. These stars are just stars in our own galaxy that we have to look through. This is an edge-on, distant galaxy. Here's the layer of gas and dust in that galaxy. The central bulge is composed of perhaps 1 billion stars, actually independent, individual points of light, which are just blurred into this bulge by our atmosphere. The next slide, please. Here's a picture that was taken recently by the COBE orbiting satellite, and one that I like very much. This is our galaxy, but what you're looking at here is the warm gas and dust which is radiating in the infrared. So this is taken with a camera sensitive to the infrared, and I like it because it really looks so much like a galaxy. The next slide. Seen head-on, we think our galaxy would look like this. A central bulge. Even in the disk, the stars are not arranged at random, but tend to clump in these long stringy arms, which we call spiral arms. The brightest features are not individual stars, but clusters in which generally new stars are being born. Stars are born from the gas and the dust. They evolve and they die. We are located somewhere on an outer arm. As I said, it takes us 200 million years. Some stars are born and evolve and die before 200 million years has gone by, and so they don't even make one revolution. The arms are not fixed. They're not a fixed pattern. The orbit of individual stars carries them into the arm, where they spend, due to the extra gravity, due to the higher mass, spend more time there, move out. and continue their orbit. It's somewhat, the arms are really the locus of points of regions of higher density, much like a traffic jam on a highway. If you looked at from an airplane view down in a region where there was a bridge or a bottleneck, you would almost always see cars there, but they would be different cars at the same time. An important feature of galaxies is that stars are very, very far apart. Relative to their diameters, you could put about 1% of all the stars. You could put 1 billion stars in our galaxy between the average separation of 2. And that means the stars don't gravitationally interfere. Next slide. This is a plot. The others were all photographs. This is a plot of our galaxy, the Milky Way, as we see it with the dust lanes, the bright stars. These two objects are satellite galaxies of our own. This is the Large Magellanic Cloud, the Small Magellanic Cloud. In contrast to stars in a galaxy, which are very far apart, galaxies, relative to their diameters, are very close together. Virtually no galaxy is isolated. We have these two small satellite galaxies visible to the naked eye in the southern hemisphere, and they are gravitationally bound to our galaxy. They orbit in paths that take these stellar systems through the disk of our galaxy. And when the gas in these systems meets the gas in our disk, there are shocks, there are gravitational tidal disruptions. These small galaxies will soon cease to exist. Successive passes through our galaxy will force them to lose energy, and they will ultimately become part of our galaxy. And we now understand that this merger process is a very active driving force in the evolution of galaxies. The next slide, please. Here's a plot of the same orientation as the preceding. Here's the Large Magellanic Cloud, Small Magellanic Cloud. The dark regions are the high-velocity neutral hydrogen gas observed by radio telescopes. And the most dominant feature is this long tidal tail of gas, of hydrogen, which has been pulled out of the Magellanic Clouds. And this is now understood as due to a previous passage of the clouds through the disk of our galaxy. The next slide. This is a telescope view of the Large Magellanic Cloud. The face is covered with these splotchy red regions, red due to the hydrogen alpha line, in which star formation is actively taking place. The Magellanic Clouds have a large population of very young stars. When I was a student, we were taught that the Magellanic Clouds were young because they had so many young stars. We now recognize that they have a population of old stars, which are as old as our oldest, but that something has recently happened to initiate this active star formation. And we think this episode, that what initiated this was in fact a passage through the plane of our own galaxy. The next slide. This is the Andromeda Galaxy, which is the largest nearby spiral to us. Can you focus that a little? It also has two satellite galaxies. Okay, we'll have to look at it out of focus. The Andromeda Galaxy and our galaxy are the two most massive galaxies in a small group of nearby galaxies, which astronomers call the local group, with a great lack of imagination, I think. So the local group of galaxies consists of Andromeda, its satellites, us, our satellites, and a few, could I have the next slide? The remainders are blotchy little systems. This is a galaxy. It has regions of active star formation. It has no dense central nucleus, and so it's very fragile, gravitationally very fragile. Whenever it comes near a larger galaxy, it's going to lose stars. This is one of the small objects which will ultimately cease to exist. The next slide. This is the center of the Virgo cluster, and this is a cluster of thousands of galaxies near to us. We are a suburban member of the Virgo cluster, and so you can see that already the structure is getting quite lumpy. We have satellites. We live in a small group of galaxies. The local group is an outlying member of the Virgo cluster of galaxies. Clusters have been very important to astronomers in recent years. The galaxies I've been talking about have been principally spiral galaxies, disk galaxies. When we look at clusters of galaxies, especially centers of clusters, we see that most of the galaxies are spheroidal, relatively featureless, and we now understand these as the end products of a merger of two disk galaxies which interact at some non-parallel angle, such that the stars ultimately make what astronomers call a star pile. And so we have these spheroidal galaxies which really dominate centers of clusters. Here's a pair of galaxies which are in the process of disrupting each other. Tidal tails like this are a very good diagnostic of a gravitational interaction. Clusters are important for several other reasons. It was in the early 1930s that Fritz Zwicky first suggested that there must exist in clusters much matter that was dark. He called it missing matter. He recognized, as soon as he had velocities of the individual galaxies, that the galaxies were individually moving very rapidly, so rapidly that the cluster should disband. But it was not disbanding, and therefore he concluded that there had to be more matter in the cluster than you could see, and that matter was in fact holding the cluster together. We know that the centers of clusters are the gravity is sufficient to have halted the expansion of the universe. So centers of clusters of galaxies are not expanding. We are expanding from the Virgo cluster, but we're expanding slower than if the cluster were not there. Astronomers often carelessly say we're falling to Virgo, but that's not so. We are expanding, but slowly. If the universe lives long enough, our expansion from Virgo may ultimately be halted, and we might then truly start to fall in. Astronomers can point to the region around the cluster in which new galaxies are at present starting to fall in. We're living in an era when clusters of galaxies are forming. The next slide, please. Well, if you go way out in the universe, this is a slide from Tony Tyson, you come to very distant clusters which are themselves acting as lenses, as gravitational lenses of the material behind them. If there was a massive galaxy just at some distance, but behind this cluster that we're looking at, then the gravitational attraction of the mass in this intervening cluster would spread the light from the background galaxy into a perfect ring. And you would see what astronomers call an Einstein ring. In fact, when the geometry is not that perfectly aligned, you get these bits and pieces of little blue arcs. And this, I hope you can see these, this is evidence. This is added evidence for the presence of matter that we don't see optically. The next slide, please. Well, what astronomers really want to know is what the three-dimensional distribution of galaxies is. And that's hard to describe because we do not, it's difficult to get accurate distances to galaxies. But to probably a zeroth approximation, we can assume that galaxies with small velocities are very close to us and galaxies with large velocities are far away from us. This is a plot. This is called a wedge diagram. The observer is here. Each one of these points represents the location of a galaxy in space. This is like a slice of pizza through the universe, going from 8 hours to 17 hours. Astronomers call the coordinate that corresponds to longitude on Earth, right ascension. It's marked in hours. This is a historical relic of when the objects would pass overhead. So this is a thin slice. And what you can see is that the distribution of galaxies is really very lumpy. There are large regions in which no galaxies have been detected. This large structure is called the Great Wall and is one of the largest structures known in the universe. This is a plot made by Margaret Geller and John Hookra at Harvard. There is now a corresponding one from the southern hemisphere, and this region in here is where the gas and dust in our own Milky Way obscures the distant universe. And in fact, it appears that this structure actually continues toward the south. Can I have the next slide? This is the New York Times from January 91 or 2. I can't read it. And it says, "New surveys of the universe confound theorists." And the confounding has to do with the fact that we believe that the structures that we see here and now are a relic of the very earliest universe. And the evidence is that the earliest universe was very smooth. And so it's very hard to understand how these large structures have originated. I used to go around saying that this didn't confound me because I was an observer. And I wasn't distracted. And I mean, it is true that I really believe what you can observe, and this is what we can observe. And about a year ago, I showed this slide in Durham, England, and a very, very bright theorist said, "But look at this, what it says in this headline, the brain may see what eyes cannot." And so I think it's a draw. The next slide. Okay, so here's a quick summary. We live in a solar system. It takes 8 minutes for light to get from the sun to the Earth. The solar system is just one of the many star systems in our galaxy. We sort of live on the outside. It takes 30,000 years for light to go from the center of the galaxy to us here. So the light that the Kobe photograph showed had left the center of the galaxy 30,000 years ago. About 3 million light years for light to cross the local group, about 30 million light years for 30 million years for light to cross the supercluster, and the supercluster is just one of these lumps in the large-scale structure. So that's a survey of what we see. And I'd now like to turn to the discussion of how you learn how much matter is involved in all of this, especially if some of it is dark. And the next slide, please. The answer starts with Newton. This is from the Principia. Mercury, Venus, Earth, Mars, Jupiter, Saturn. The numbers are the numbers of days, 365 days to orbit the sun. And the distances from the sun of these planets in terms of unity, or 100 million for the Earth. The next slide looks like this. If you plot the orbital velocities of the planets as a function of their distance from the sun, you see that the planets that are very close to the sun, Mercury, go very fast, And the velocity, these are the orbital velocities of the planets fall off as they go further and further from the sun. What Newton understood when the apple hit him on the head was not that apples fall, because everybody knew that apples fall to the ground, but what he understood was it was the same force of gravity that pulled the apple to the ground, that pulled the Earth around the sun, pulled the moon around the Earth, and we would now say pulls the Earth, the sun around the center of the galaxy. The forward motion of the Earth around the sun is so great that although we are continually falling to the sun, we're never hitting it. We can't hit it because our forward motion carries us in the forward direction, and the sun is curling under us, if you like. So if you know the distances and the velocities, you can calculate how much matter there is in the sun. And so you are using each of the planets as a test particle in the gravitational field of the sun. What Galileo knew when he dropped the feather and the lump of coal or something from the Tower of Pisa was that it doesn't matter what the test particle is. It doesn't matter whether this is a planet here or a bit of dust or an elephant or another sun. If you just have something whose velocity and distance you can measure, you can interpret from that how much matter there is interior to that position. And this is what we do when we attempt to determine how much matter there is in a galaxy. Could I have the next slide? So some years ago, with my colleague Kent Ford, who is here tonight, we embarked on a long-range program to measure the motions of stars in galaxies. Much of the work was done at Kitt Peak. This is a picture of Kitt Peak. Next slide. This is to prove to you that sometimes even radio astronomers go to optical observatories. This is the Solar Telescope at Kitt Peak. This is Bertil Lindblad. This is Mort Roberts. Could I have the next slide? This is even worse. This is Lowell Observatory with the Carnegie spectrograph, Carnegie image tube. This is Kent Ford. This is Vera Rubin. This, I think, is 1965. And I think we're trying to get ready to observe. The next slide. This is Chile, the CTIO national facility, as Kitt Peak is also, run by a consortium of universities funded by the National Science Foundation. The next slide is the Las Campanas Observatory of the Carnegie Institution. This is a 100-inch telescope, presently the largest telescope there. The next slide shows a picture taken about 2 months ago. Here are two holes in the ground in which two 6.5-meter telescopes are to be built. The next slide. So, what Kent and I did was pick some galaxies that were moderately inclined. Stars are orbiting in the sense that the arms are trailing, so stars are orbiting in this sense. We use this instrument called a spectrograph with a grating which disperses the light into its constituent frequencies, like a rainbow. And we use a long slit so that each point on the galaxy, we just make a skinny cut across the center, reproduces in the spectrum this line of hydrogen alpha. And so this point comes from here, and this point comes from here, and this stripe comes from the center. And by measuring the location of each one of these knots on the spectrum, we can determine how rapidly each point in the galaxy is moving. The next slide. This is a spectrum. This was done initially with an image tube, an electro-optical device, and we recorded these on photographic plates. It's now done with the CCD device, but this is the kind of spectrum we come home with. Virtually all the lines you see in here, all the lines crossing the spectrum, come from the night sky, the OH molecule in the Earth's sky. So even though we go observing on nights that we call dark, the radiation from the night sky is this intense. The one exception is this line across here, which is the line of hydrogen alpha in our Earth's atmosphere. And here is hydrogen alpha in the galaxy. So as you can see, the hydrogen alpha in the galaxy is displaced by this amount. This is red, this is blue, displaced this much from the night sky. So that's the evidence that the universe is expanding. This galaxy is moving away from us, and its hydrogen alpha line is displaced toward the red. But you can see on one side, the galaxy velocities are low with respect to the center, high on the other. And this is due to the rotation of the stars, and that's what we're attempting to measure. Next slide, please. So in every case, we get lines which look something like this here. Every place we cross a spiral arm, we see the hydrogen. Next slide, please. And then take it back to the lab and measure it, and make a plot of the rotational velocity as a function of distance from the center. And what you see, and what was unexpected, is that the velocities, as far out as we can measure, do not in fact fall. The light from this galaxy would predict that the rotation velocity should have gone up, turned over, and then fallen way down. And the fact that they didn't, we interpret it as meaning that there is more matter in the galaxy that we can see, and the velocities of these stars are remaining high in response to the gravitational attraction of this matter that we don't see. The next slide. And here's a set of just 5 galaxies. In every case, whether the galaxy is truly tiny, as this one, or very large, as this one, the rotational velocities remain high. The next slide. So these are the questions that we'd like to be able to answer. And in fact, we can answer very few of them. The question, does it exist, is generally answered affirmatively. The only way we could explain the observations without dark matter is to say that Newton's laws do not hold over distances this large. And the scientific community is really reluctant to say that Newton's laws don't hold, although there are very capable scientists attempting to make relativistic cosmologies which are altered, and if they are successful, we may have to reconsider. But if you, ignoring Newton's laws, then we have evidence that it exists. We know that it's in clusters of galaxies. We know that it's in individual galaxies, and I want to show you more of that evidence by going to the view graphs. So thank you for the slides. So this is what we have. Newton's laws, for those of you that remember your high school physics, tell you that the mass interior to any r can be calculated if you just know the distance r and the velocity squared. So if for any test particle at distance r from the center of a mass m, the mass can be calculated with a constant. We have a rotation curve. We've plotted here rotational velocity versus distance from the center. Rotation curve that looks like that. The light in the galaxy would predict that. And so this is the contribution to the velocity from the dark matter. And therefore, if you want to study the dark matter, you want to go to the largest radius that you can possibly get. And the other comment I wanted to remember to make was that clearly the contribution to the dark matter gets more important as you go to larger and larger distances. Well, here's a plot from 1975, Roberts and Whitehurst. This is the Andromeda Galaxy. The optical observations, which Kent and I had made earlier, looked like that, but ended here. But radio astronomers are lucky. Many galaxies have very large hydrogen disks, which extend beyond the optical galaxy. And in 1975, the rotation velocities of Andromeda could be studied almost twice as far as they could optically, showing that the velocities still remained high. So even in the region where you saw virtually no optical light at all, the gravitational field was not falling off very rapidly. But that was not the earliest. 1972, Rogstad and Shostak had published a series of papers, a series of rotation curves for 5 galaxies, also very flat, but were not really believed. Partly, I think, because people worried about side lobes and whether the beam size was contributing to artificial flatness. That was 1972, but that was also not the first very flat rotation curve. The earliest rotation curve that I know of was 1959 by Louise Volders in the Bulletin of the Astronomical Institutes of the Netherlands, in which she looked at the rotation velocity of M33, a smaller spiral galaxy in the local group, and got this exceedingly flat rotation curve. The blue points are what the optical astronomers had measured at that time. The red curve is the 21 centimeter curve, and that really passed without any notice whatsoever. More recent work, here's an image from 1992, of the galaxy NGC 628, a beautiful spiral galaxy, which we would call a large spiral optically, but the 21 centimeter neutral hydrogen disk extends 3 or 4 times as far, and you can therefore get velocities correspondingly farther. Sometimes nature is very good and gives you all kinds of presents. Here is a galaxy IC2006, which optically looks like this: a spheroidal galaxy. It is rotating such that this part is going away from us, this part is coming toward us. But it is enveloped in a larger ring of neutral hydrogen, which means that we can get rotational velocities out farther. The neutral hydrogen happens to be going in the other direction. And we see that more and more now. Galaxies in which several disks may exist, some going one way, some the other. Additional evidence that galaxies have been formed through a merger process. Sometimes optical astronomers are a little bit lucky. Here's what we call a polar ring galaxy. A normal galaxy encircled by a ring. We can measure velocities in the ring as well as in the disk, and if we fit them together, we still see that the rotation curve remains flat. As far out as we can measure, the presence of dark matter seems to exist. I want to take just a couple of minutes and show you what we can do for our own galaxy, where enormous efforts have been made to go further and further and further. The first paper I know of is one that I did with my students at Georgetown in 1962, where we looked at the stars available in the literature, and we asked, what did the rotation curve beyond the sun look like? So we plot the velocity here, the distance here with the sun here. We found that it looked very flat, and we wrote that beyond the solar circle, the rotation curve is approximately flat, and the decrease in rotational velocity expected for Keplerian orbits is not found. That was 62. In 1993, people were still trying to do the same problem. Here is a plot. This is the cover of the Astronomical Journal in 93. This is the location of the sun. It's very hard to find stars very distant from the sun in the anticenter, but what little evidence there is certainly appears to show that the rotational velocities are remaining flat. However, we can do better than that. We can use the Magellanic Clouds as a test particle. Knowing the orbit of the clouds, which we do now quite well, we can use them. The clouds are at a distance of about 50 kiloparsecs, about 5 times as far from the center of the galaxy as we are, and the mass continues to increase all the way out to the Magellanic Clouds. So if you go out as far as the Magellanic Clouds, we have a mass interior to the clouds of about 6 times 10 to the 11th. At the position of the sun, the mass interior is about 1 times 10 to the 11th solar masses. But we can do even better. We have lots of satellite galaxies, lots of globular clusters. Lyndon Bell and Kulesa in 92 used 43 of these to go out to a distance of 230 kiloparsecs, about 5 times the distance of the Magellanic Clouds, and got a mass of some 10 to the 12th solar masses. And ultimately, of course, someone, in this case Jim Peebles, asked the question, how much mass is there in the local group? He assumed that at the origin of the universe, the individual galaxies were at rest and have now come together by their gravitational interaction, and has required that they now have the positions and the velocities that we see. In doing that, he gets a total mass for the Milky Way of 2 times 10 to the 12th solar masses, and a mass of the local group of 2 times 10 to the 13th. The most interesting thing that comes out of this is that over the local group, we have only about 1/10 of the amount of matter that would be required to close the universe. So the local group, although it is a group and we think therefore should have a higher density than the surroundings, the amount of matter in the local group, both in luminous and in dark matter, as understood from the gravitational motions of these dozens of galaxies in the local group, the density is still only about 1/10 of the closure density. So based on the local group, we would say that we live in a universe of low density. So here's a summary for our own galaxy. Interior to the sun's orbit, we have about 10 to the 11th solar masses. Interior to the Magellanic Clouds, about 6 times that. Interior to the globular clusters and satellites, some 10 to the 12th. And the local group gives us a couple times 10 to the 12th. And therefore, we can make a plot in which we plot radial scale in this coordinate, the amount of matter, mass, the detected matter, gravitationally and optically relative to its light, or over here the density relative to the closure density. So the Milky Way, as we go to larger and larger distances, out to this farthest distance and then ultimately the local group, continues to grow. The amount of matter in the local group relative to the amount of light just grows and grows and grows out to this point. And the question that cosmologists would like to answer, and I think most people would like to answer, is, do we live in a universe that will expand forever, or will the gravitational attraction of all the matter inside of the universe ultimately halt the expansion and start it recontracting, or is it just exactly flat? Do we live in a universe in which the density is just the closure density so that it will sort of halt the expansion and just kind of sit there? And so what we really want to know is, if we go to larger and larger scales, will this line continue to grow up to 1, or will it in fact turn over? And the evidence that's been gathered most recently, a lot of it from X-ray observations of clusters, is in fact that it does turn over. We can observe many of the very large clusters in X-rays, and it turns out that the clusters are, the dominant mass in the clusters is very hot gas. Clusters have about 10 times as much hot gas as they have in optical galaxies, but they still have densities relative to the closure density that just sit around here. And it's based on that kind of evidence. Let me show you a plot for the Perseus cluster. This is distance in the cluster. These are monumental clusters. Their density, the density in luminous galaxies falls off like this. Dark matter is more dominant than the galaxies. The X-ray gas becomes even more dominant as you go farther out. The total density implies a mass relative to its luminosity of about 100, which puts it right about here. And so we are left, I think, with evidence that clearly indicates that at the present time, there are no observations that imply that we live in a closed universe. Now, the problem is that based on the most accepted cosmologies, theorists would like the closure density, the amount of matter in the universe to just match the closure density. And before quitting, I should just point out that theories of the Big Bang tell us that the amount of conventional particles in the universe, the amount of normal atoms that make up atoms and molecules and make up all of us and the Earth and all the stars and galaxies, requires that, and that conventional matter is called baryons. The number of baryons in the universe implies a closure density also of about 1. So if we live in a universe which is closed, if the density of the universe is high enough to halt the expansion, then that matter must be unconventional. It must be unlike the matter we have so far detected in the universe. And that's the problem that cosmologists are attempting to, cosmologists and particle physicists are attempting to see whether they can build particle detectors to detect non-baryonic matter that could be the constituent that closes the universe. Well, in putting this together, this is really for my astronomer friends, I thought that we perhaps should recognize how lucky we are that the matter is dark. This is a plot of the sky, and here is the Andromeda galaxy. And we know that the halo around Andromeda goes out about that far. And so if the matter were not dark, we would see when we looked at the sky an Andromeda that was bigger than the moon. And if each other galaxy on this plot had its halo not invisible, we would know much less about the universe, because the brightness of this matter, which we presently can't see, would make the night sky so bright that instead of having someone standing up here and talking about dark matter, someone would be standing up here trying to talk about how we can see what's hidden in this bright light due to all the glowing halos of galaxies. So I think we should consider ourselves very lucky. And I will close with a favorite cartoon of mine, which says, lots of things are invisible, but we don't know how many because we can't see them. Thank you very much.